This is a seminar talk that I first delivered today at Bridgewater State University's Math Department seminar on March 7th of 2013. You'll notice it's snowing out the window behind me. We're supposed to get about 6 to 8 inches, so a lot of campus, I believe, is beginning to shut down. So let me make sure I get this recorded for posterity before everyone leaves for the weekend. So this is a talk titled Galois Theory into Practice, a Cubic Workout. Really, my motivation for doing this seminar is I'm not really hoping to break a lot of new ground, and those of you out there that are algebraists, unlike myself, probably already know a lot of what I'm going to present here in this seminar. But when I decided this semester to teach second semester abstract algebra, I was really running toward a subject that I've spent a lot of my mathematical career running away from. I'm not an algebraist by any stretch of the imagination, so a lot of what you see here, you might say, oh, of course, that's obvious, everyone knows this. But when I have to teach this subject to undergraduates, one of the things that comes up very often when you start talking about Galois theory is Galois made these big promises about how this was the way to solve polynomial equations. The purpose of Galois theory is that you can actually use it to help find solutions of polynomial equations, and that if your Galois group is a solvable group, then those solutions can be found in terms of radicals, simple radicals, and the original coefficients of the polynomial, which is great, and which is also surprising when you find out that those radical solutions actually run out once we get to polynomials of fifth order and higher. And that's all well and good, but I started casting about, not having taught the course before, looking for a specific example of somebody that had taken Galois theory and used it to very explicitly construct the solutions to a polynomial equation, showing exactly what role is being played by the Galois group and by the quotients of a solvable Galois group, and how all of this process is done in practice in a very specific example. I spent quite a bit of time looking for a specific example, and not coming up with one, I decided I should just try to make one up myself. So we're in the unique position that this is a seminar, this is an hour-long talk in principle, that's dedicated completely to solving a single equation, and it's a very simple-looking equation. It's a cubic equation, t to the third minus t minus 1 equals 0. This is not to say that Galois theory is the only method by which this polynomial's roots can be found, but what I wanted to do is really to expose how Galois theory can help us to think about the solutions to this equation. And it's a bit of a weird kind of a talk for me. As a geometer, I'm used to giving talks that are more sort of visual and conceptual in nature, spend a lot of time talking about ideas and concepts and theory. And yet, this is a talk that's by its very nature very computationally oriented. So we're going to do a lot of computations. But I'm going to keep coming back to, okay, what is this computation telling us about the structure of the groups that tell us something about this polynomial? So what is the big framework of Galois theory, and how does it help us to do these computations and to put these computations into an abstract algebra framework that gives us something that we didn't have before Galois did what he did? So in a sense, I'm kind of taking a very classical approach to the solutions of this equation, but at the same time, we're going to be using some of the language of modern group theory. And unlike other people that give talks on Galois theory, I'm going to specifically stay away from using words like field extension, automorphism, Galois group, all of that stuff. I'm going to stay away from that terminology because I want this to be as first principles as we can manage it to be, and yet still have that abstract algebra component to it. So this is a talk dedicated to the solution of one equation, t to the third minus t minus 1 equals 0, and paying attention specifically to the role that's being played by the Galois group structure along the way. So what does it have to do with the process that we actually employ in solving this equation? So let's get going. So again, this is a talk that is a direct response to what I've noticed is kind of a lack out there of specific examples of how Galois theory actually helps us to find the solutions of certain polynomial equations. So again, this talk is going to be entirely dedicated to putting that theory into practice in the case of a specific cubic equation, and the cubic equation that I want to look at is this one. T to the third minus 3t minus 1 is equal to 0. So I'm using t as my indeterminate variable. My students sometimes ask me why I'm so fond of t in this role. Well, one of the reasons is that if I use t as my indeterminate, then I can keep other familiar letters like x, y, and z. I can keep x, y, and z reserved for the roots. So let's suppose that x, y, and z, in the case of this talk, denote the solutions, the specific roots of this equation that satisfy t to the third minus 3t minus 1 is equal to 0. And in principle, those solutions in general, are going to be complex numbers. But one of the interesting questions of Galois theory is what kinds of numbers are they really? I mean, do we have to have all of the complex numbers in order to craft these solutions? And in general, the answer is no. And in this specific example, we'll see that the answer is no. But this is just to lay down our notation, that when we say t, we will always be thinking about the indeterminate, and that x, y, and z we'll think of as our roots, our solutions, just so that we keep that straight for the balance of what we'll be doing here. So there are a lot of things that we could do to solve this equation. In particular, if we could somehow be so lucky as to factor t to the third minus 3t minus 1 equals 0 into a pair of factors and split that apart, that would work wonderfully, as any first semester high school algebra student can likely tell you. But as it happens, this is not a factorable polynomial. There are a variety of different ways that we could justify that. We could try reducing the coefficients, modulo, maybe modulo 4 or something like that, and showing that the resulting polynomial does not reduce in any meaningful way. We could use Eisenstein's criterion, where we would go looking for a prime that divides certain coefficients. That actually wouldn't work here because our constant term is equal to 1. But that's not where I hope to spend our time in this talk. So as far as we're concerned, we're going to pursue a path that doesn't involve factoring this polynomial. And in fact, this polynomial is irreducible over the rationals, so there's no factorization that's going to help us in this example. Of course, if we were so inclined, we could also go after a numerical approach to solving this equation. So we could just get it over with and put in a graph. And so we would get a graph, and it would look something like this, and we could say, well, using numerical methods, maybe Newton's method or something like that, we could get some numerical approximations to the three roots. Notice, by the way, in this graph that all three roots of this polynomial equation are indeed real numbers. So we could use numerical methods, but as I'm fond of telling my calculus students, that approximate answers are only approximately correct, so we're going to stay away from numerical methods just for the sake of this seminar, although certainly they could be used with quite a bit of success to give us approximate answers in a more general setting. One of the sort of canonical ways to solve a cubic, especially a cubic that's been set up like this one, is to use a trigonometric substitution. And that trigonometric substitution would come in the form of some kind of a triple angle formula, maybe a triple angle formula for cosine or something like that. And that would be remarkably effective, but I want to stay away from that. One of the reasons I want to stay away from that is that as soon as you drag trigonometry into the picture, it's no longer clear that your roots, that your equation, that everything remains algebraic. In other words, the trigonometric functions, because they're transcendental functions, they kind of blur the distinction of what's really going on here. So I'm also going to stay away from trig substitution. Probably the most powerful tool that we could think about using is the cubic formula. There is actually a formula in the coefficients of a cubic equation that can tell us the roots of a cubic equation. Just like there's a formula for quadratics, there's also a similar formula for quartics. So we could go after the cubic formula. So why am I not going after the cubic formula in this talk? Well, again, the cubic formula is a formula involving only radicals and the rational coefficients of my cubic polynomial. But where that cubic formula comes from, in other words, if we wanted to try to go along a path of discovering the cubic formula, chances are we would be doing a lot of what we're going to do in this talk anyway. That to discover the solutions of a cubic equation in general and what formula we can use in the coefficients to get its solutions, we would do the same kind of Galois theory arguments that we're going to end up doing in our specific example here anyway. So what Galois theory does, so at its heart, Galois theory explains how formulas like the cubic formula arise, and it does so in an interesting fashion by looking at what happens when we take the roots, again, x, y, and z are what I'm going to call the roots here, and permute them back and forth. So how many different ways are there to permute the three roots x, y, and z? Well, naturally, this is where the group theory aspect comes into it. So each different permutation of x, y, and z that I choose corresponds to a different element in the permutation group on three symbols. And I'm going to denote for the sake of our talk today, if I swap the first two variables here, I'm going to call that xy in cycle notation. If I swap the second with the third, xzy, I'm going to call that yz, or zy if you like. And we could list the other three over here also. Swapping x with z would give me zyx. And then we have the three cyclic permutations, x, y, z, where everything takes one step to the right. So x goes here, y goes here, z ends up back there. And then finally x, z, y, in which everything takes one step to the left, and so that becomes y over here, z over here, and x over there. So these are the 6 different ways to permute the elements in question, and those 6 different ways together form the symmetric group on 3 symbols. So already we're seeing where group theory might help us to do this in some way or another. But the question, of course, is what does switching the roots around have to do with anything? Specifically, what in the world does it have to do with the solutions of this equation? And that's the big surprise of Galois theory, and it's part of what makes Galois theory mathematically the greatest story ever told, in a sense. So here's the main idea. I have an equation, and I want to know its solutions x, y, and z. So what I'm looking for, really, is I'm looking for the values of 3 specific polynomial expressions in x, y, and z. I'm looking for the values of these 3 polynomial expressions. So these are polynomials in x, y, and z. Their coefficients happen to be 1, so they happen to be rational numbers. Anyway, so these, if we think of them as polynomials, and then think about, well, what's going to happen to any one of these polynomials if I swap the roots around? So if I swap x with y, then this polynomial x is going to turn into the polynomial y, which in principle could have a different value than x originally had. So permutations of these of the variables in these 3 polynomials will in general change their value. The only way in which permutations would not change the values of these polynomials is if all of them happen to have the same value. And that's not, we'll find out that that's not going to happen here. So we're going to start from a situation where what I want to know are the values of these 3 polynomials, and a situation in which all of the permutations that we can do matter to one of these polynomials or the other, in the sense that they're going to change the value of one or the other of these polynomials that we're interested in. But on the other hand, there are other polynomials in x, y, and z whose values don't care if we apply a permutation to those 3 variables. For instance, the ones I have listed on the left here, x plus y plus z, x squared plus y squared plus z squared, x times y times z, any permutation of x, y, and z is going to give us the same value back. Gives the same value. So this is pretty obvious, right? For instance, in x plus y plus z, if I swap x with y, I'm going to get y plus x plus z, which, because addition of complex numbers is commutative, that's going to give me the same value as x plus y plus z did. So these polynomials over here have been crafted in a very careful fashion that makes it so that their value doesn't depend on which order we put their variables into them. So any permutation of x, y, and z is going to give each of these polynomials in x, y, and z this very same value. So these are 2 very different sides of the coin here. On the one hand, what we really want to know are the values of these polynomials in which permutations are very important. Permutations change the value of the polynomials x, y, and z that I'm really interested in finding. And on the other side of the coin, we have these polynomials for which permutation of their variables does nothing to their value. So the name of the game is how to get from left to right somehow. How to use the values of these symmetric polynomials to give us somehow the values of these non-symmetric polynomials, like x, y, and z, the roots. So here's the key. The key is that the values of the polynomials on the left, the completely symmetric polynomials, those are values that we can directly compute from the coefficients of our polynomial. It's actually even better than that. They're values that are rational functions of the coefficients of our polynomial. In other words, we don't have to take any square roots. We don't have to do anything fancy. All we have to do is add, subtract, multiply, and possibly divide coefficients of our polynomial to find the values of these things on the left. Whereas the things on the right, we don't know that, but we'd like to somehow use the values that we can directly compute from the coefficients on the left to tell us something about the values that we get on the right. So what does that look like? Well, keep in mind that when we say that a polynomial is completely symmetric, what are we really saying? We're really saying that its value is the same if any permutation of those 3 symbols is thrown at it. So I've listed here all of the different permutations that keep the values of those polynomials on the left the same. And here I'm listing all the permutations in the symmetric group on 3 symbols. Whereas meanwhile, over on the right, where any permutation that we do to x, y, and z can in principle change the value of one or more of these expressions, x, y, and z, the roots, over here we might say that the symmetry group of this list of three polynomials is really the trivial group. There's nothing I can do that's non-trivial to this list of x, y, and z that will keep all the values of these three the same. So this kind of frames us into a group theory context, where instead of thinking about polynomials, we're thinking of those groups which keep our polynomials' values the same. We're thinking of the symmetry groups of these polynomials. So what we're really looking for somehow is a way of getting from the fully symmetric case, where we know everything, where we can compute the values of these, and get all the way down to the completely non-symmetric case, where we can say what the values of x, y, and z actually are. But here's the issue with that, is if we try to take this step all at once, in other words, if we try to set up some nonlinear system that can tell us what the values of x, y, and z are if we solve it, using the values of the symmetric polynomials on the left, actually directly solving that nonlinear system of equations turns out to be no simpler than solving the original cubic. In other words, if we wrote out that nonlinear system and reduced it as much as we can, we would eventually come down to a cubic equation, which is completely equivalent to the original cubic equation that we're trying to study. So directly solving, going all the way down from fully symmetric down to the roots, is not really an option in general. So what we'd like to do is we'd like to take a baby step. We'd like to break down that leap from fully symmetric down to the values of the roots themselves by putting some step in the middle. And if there were a step in the middle, that would correspond to some polynomials in x, y, and z for which some permutations might change their value, but other permutations might preserve their value. And the name of the game here is we need to find a way to construct those polynomials in the middle, those polynomials for which permutations matter, and then see if we can nevertheless compute the value of those polynomials in the middle using the value of the polynomials on the left. So just to summarize what it is we're trying to do here, we'd like to find some polynomials that are symmetric under some permutations but not other permutations. Then use the values of the symmetric polynomials, which we can compute directly from the coefficients of our original, to find the values of these partially symmetric polynomials, and then use the values of those partially symmetric polynomials to determine the values of our totally non-symmetric polynomials x, y, and z, the roots. If we can find the values of those three things, then we've found the roots of our polynomial. Now, what does that look like in group language? In group language, that looks like putting an intermediate step in between the group S3 of all permutations of three symbols and the trivial group down here at the far right side. We might be able to think about this as though we are putting a subgroup in between S3 and the trivial group. And there are a variety of choices that we could make. There are a variety of different subgroups that S3 has. And so one of the important tasks for us is going to be to choose a subgroup that can help us to make that leap. And once we know what that subgroup is, that's going to be the subgroup that determines the permutations that don't matter. In other words, these polynomials here in the middle are going to be H invariant. So whatever permutations happen to be in H, those will be the ones that keep the values of these polynomials in the middle the same. And those polynomials that are not in H, those permutations that are not in H will change the values of polynomials in the middle in general. This connection here is usually called the Galois correspondence. It's kind of the most important connection in the entire theory here. To be able to connect a group of permutations, so a subgroup of some Sn, to connect it with the space of all polynomials whose value remains invariant under that group of permutations. That correspondence ultimately, I promised I wouldn't use the word field, but I'm going to use it really quickly here, ultimately leads to a theory of invariant fields, where we have a field that's invariant under this action. So that's the setting that we want. So I want to take a step back here because this is going to be a very computational talk, and there's a really brilliant idea in here that I want to make sure doesn't get lost in the shuffle. So how in the world are we going to come up with a polynomial for which some permutations matter, some permutations change its value, but other permutations don't change its value? The analogy I'm going to use here is an analogy that comes very near and dear to my heart because I watch an awful lot of the Food Network. And on the Food Network, as you know, there's a bunch of celebrity chefs, and those celebrity chefs tend to have little rivalries between one another. So, let's just take an example where I've got a few of my favorite celebrity chefs. So let's maybe get Alton Brown in here, and then maybe Bobby Flay, just for the sake of argument. So here's Flay, and then let's put in, some chef whose name starts with C. There aren't that many on the Food Network, but one of the Iron Chef's names is Kat Cora, so here's Kat. So I got 3 chefs, A, B, and C. And now let's suppose that these chefs all sit down to a table, and they're going to judge a dish. Well, each of these chefs has, being a professional chef and being on the Food Network, they have a lot of interesting friendships and rivalries among the other chefs on the Food Network. So let's suppose for the moment that we blindfold all 3 of them. They all taste a dish. And then they're going to give that dish a rating. So they're going to give that dish a score. And the rules of this game are that each chef really likes the chef that's sitting to their left. So they're going to, for a given dish, they're going to rate that dish higher, I guess, than the chef to the left of them. And likewise, really doesn't like the chef sitting to the right. So they're going to give a lower rating to the dishes that the chef to the right likes. So let's suppose for the moment that one of these 3 chefs actually makes the dish that's sitting on the table. So they're all going to eat the same dish, and this dish was cooked by one out of the 3 of them. And they all taste, and they all write down their score. The question is, do we know from the basis of those scores whose dish is underneath the cloche on the table? So do we know whose dish they tasted just based on one rating? Well, let's imagine for a minute that this is a Chef Bobby dish under the table. So this is B. Now, Kat Cora, because she is sitting, because Bobby is on her right, she really doesn't like Bobby, so she's going to give him the lowest possible score, which, let's make that a 1. Meanwhile, Alton Brown, Bobby is to his left on the table, and so Alton really likes Bobby, so he gives him a 3. And then Flay himself, being as modest as ever, is going to rate his dish a 2. So if we just do this, and then we look at all the scorecards, we would know exactly whose dish is on that table. Because Bobby is sitting in the 2 spot, and he gave it a 2, then we know it's his dish underneath there. So in general, yes, we can tell whose dish is there. But let's suppose that we don't want that. Let's suppose we want to come up with a rating system in which, at the end of the day, we don't know whose dish was under that cloche on the table. What could we do to accomplish that objective? Well, here's an idea. Let's suppose after the chefs get a chance to taste everything, that we make them all change places. So we take Bobby Flay and we move him over to this position. So we move him, everybody takes 1 step to the left. So we'll take Alton Brown and move him back into Bobby's old space, and we'll take Kat Cora and move her up to the top of the table. Okay. So after the first tasting, now we've rotated everybody around. Okay. But now they're going to taste that same dish again, and when they taste that same dish again, Bobby's going to give it another 2, Kat's going to give it the same 1 that she originally gave it because she doesn't like him. And Alton likes Bobby, so he's going to give him a 3. Now if we look at everybody's scores, well, we still have different numbers on different cards, and if we wanted to, we could probably tease out whose dish is under there, just based on a knowledge of the structure of the game that's going on. So the chefs actually still matter in this example. So if we want that not to be the case completely, we should have the chefs do this one more time. Everybody take 1 more step to the left. So Bobby moves up to the top now, and Alton moves over to the left, and Kat moves into the bottom right. And one more time, chefs rate the dish at the table. And so Bobby gives himself a 2 because it's his dish. Alton really likes him, so he gives him a 3. Kat really doesn't like him, so she gives him a 1. Okay. Now take a look at the scorecards. Each one of the scorecards, even though it's been visited by 3 different chefs, has the same numbers on it, even if they happen to be numbers in a different order. So what we might do, we could look at this right now and tell, again, whose dish was on the table, because we could look at whose dish, whose scorecard has the 2 in the first spot. Right? So because we knew that Bobby started this whole thing over here, we could tell for sure that it's his dish. So if we want to obscure that piece, what we should do is total up everybody's scores. So let's add up 2, 3, and 1, maybe. Get 6. And if I do that on all these scorecards, now take a look at what's happened. Once we obscure the individual ratings and keep only their sum, now we have no idea whose dish was just tasted. So through a process of moving the chefs around the table once, in other words, rotating the table 120 degrees and then 120 degrees again, and having them record their scores each time, and then totaling up the scores on each of the scorecards, now we can't tell whose dish was under there. So that's the metaphor that we're going to use to do a very interesting procedure on the next slide here. What does this have to do with polynomials? Suppose that I want to make a polynomial that's invariant under an action of some finite group, and let's take the group Z mod 3, so the cyclic group of order 3. How might I do that? Well, let's suppose that we take some polynomial, any old polynomial really, it doesn't matter, so who knows, x to the third y squared or something. I put that polynomial down on the table underneath these cloches and have all the chefs taste that dish. And then what we're going to do is, at each one of the spots on this table is going to be one of the elements of my group. So maybe there's the trivial element over here, the forward 3 cycle over here, the backward 3 cycle over here. And then each time, that group element is going to look underneath their cloche at their plate at x cubed y squared in this example, and they're going to write what they see. So the trivial permutation is going to see x cubed y squared. The permutation that moves 1, 2, 3, in other words, this is everything takes a step to the right. Instead of x, we're going to end up with z, and instead of y, we're going to end up with x. So this is going to be z cubed x squared. And likewise up here, 1, 3, 2, this is the backward cycle, x, z, y. Where we used to have an x, now we're going to have a y, so it's going to be y cubed, and where we used to have a y, now we're going to have a z. We'll have y cubed z squared. And in this round, each of the scores is different. So then we take these group elements and we make them move around the table. So we'll take the trivial element and move it over to here. We'll take the forward 3 cycle and we'll move it over to here. And we'll take the backward 3 cycle and we'll move it over to there. And then again, ask each one of these group elements to rate what it sees, to permute the polynomial that it sees. And so we'll end up with y cubed z squared over in this position. We'll end up with x cubed y squared over in this position. And we'll have z cubed x squared in this position. And then after all of these permutations, take one more step around the table. So backward permutation comes over here, and the trivial permutation ends up going up to the top. And they do it one more time. We're going to end up with x cubed y squared up there, and we're going to end up with z cubed x squared over here, and we'll have y cubed z squared over here. And then we have the same 3 things on everybody's scorecards, and adding them all up, we're going to get the same thing everywhere. And so what we get is something called a Reynolds average. This process is called Reynolds averaging, and really it amounts to adding up the orbit, adding up along the orbit of a polynomial along every element of a permutation group, along the action of every element of a permutation group. So we can add them all up and we get something that's invariant under the action of that subgroup of permutations. We also have the option, if we choose to use it, of multiplying instead of adding. So there's no reason that I have to sum here. Instead, I could choose to do a product, and I would still get something which was symmetric under the action of our subgroup of permutations. So this is a technique that we're going to use to help us build up some symmetric polynomials. So let's take a look at where we're at. This is a slide you're going to be seeing a lot of for the rest of our talk. So we have, from the point of view of groups, we have the full group of symmetries on 3 symbols up here. That's going to correspond to those polynomials that are fully symmetric, things like x plus y plus z. Meanwhile, down here on the right, we have the trivial group, standing in for the polynomials that have no symmetry to them whatsoever, like x, y, and z themselves in general, but it also contains other linear polynomials like 2x plus 3y plus 4z. Then we have this stuff in the middle, the partially symmetric polynomials. And corresponding to that partially symmetric set of polynomials is going to be some subgroup, h, of the symmetric group on 3 symbols. So here's a question. If I have one of those polynomials, how many different values can it possibly take on? You'll note that a fully symmetric polynomial, when the symmetric group acts on it, can only take one value, because every element is going to give it every element of Z3, every permutation is going to preserve that value. Meanwhile, in principle, something which has no symmetry to it at all might take on a different value for every different permutation in S3. So it could take up to 6 different values. So what about a partially symmetric polynomial? How many different values might it take? So here's an example. suppose I take the polynomial, which is just x, and we look at how many different values that x can take on. Well, if I do nothing, if I do the trivial permutation, then I get the value x back again. But I also get that same value if I apply the permutation yz, because this polynomial doesn't depend on y and z. I can interchange y and z with no penalty. On the other hand, if I apply a permutation that turns x into y, like the permutations on this row, then the value of that polynomial can in principle change. It can become y. And if I have a permutation that turns x into z, then I could get a different value as well. So this particular polynomial, even though polynomials in this class can in general have up to 6 values, this polynomial only takes on 3 different values in general, at maximum at least, again, assuming that there are no repeated roots for our polynomial. Okay, so then what next? Let's suppose that we look at a subgroup of S3, and for our sake, I'm going to look at the subgroup which consists of these 3 elements, the 3 cycles. So this is the subgroup of S3, which is of order 3, and it's generated by either of the forward or backward 3 cycles. And so that's going to be my intermediate group for the sake of our talk today. And the invariant polynomials of that can take on really only 2 different values. Why 2? Well, because a polynomial that's invariant under Z mod 3 is going to take the same value for each of those 3 elements in Z mod 3, the only way to make it take a different value is to choose a permutation that's in the non-trivial coset in the quotient of S3 by Z3. And that quotient has only 2 elements in it, and so each different value corresponds to one of the different elements in the quotient group. In other words, every different coset of Z3 is going to give me in principle a different value for a polynomial that's invariant under that Z mod 3. So let's return now to the question of which polynomials are there actually in the middle. So to do that, we're going to go back to this Reynolds averaging process, and you want to do so in as basic a way as possible. In other words, I want to put a polynomial underneath the cloches on the plates here that is as simple as it can be. So I might think about starting with, I don't know, x. But the problem with that is that x is not invariant under the Z mod 3 action. So I don't want to put x under here. What about xy? Well, xy is great to put on the table here. The problem is that if we were to compute the Reynolds average of xy, we would get something that wasn't just Z mod 3 invariant, it's actually all of S3 invariant. So that turns out not to be what we want here. What I want to do is put something on the plate that's going to notice a transposition, but which will not notice a 3 cycle at the end of the day. So instead of just x times y, I'm going to take one of those factors and square it, so that we can tell the difference between x's and y's in this polynomial. So if I start with xy squared, and I put that on the plate, and I start with the elements of my Z mod 3 sitting around the table like this, then my scorecard is going to read xy squared. Over here, 1, 2, 3 is going to turn this into, well, in place of x, now we're going to have z. In place of y, now we're going to have x. So zx squared. And then up here, I'm going to have yz squared. Then everybody rotates places, and since we end up getting the same total on every card anyway, I'm just going to record what happens on the card down here at the lower right. When 1, 3, 2 comes down to this seat at the table, it's going to be yz squared. And then when we rotate one more time, and we bring the other permutation around, we're going to end up with zx squared. So that the Reynolds average of these ends up being the polynomial. If I Reynolds average xy squared underneath this z3 action, I get xy squared plus yz squared plus zx squared. And you can check directly for yourself that this is indeed invariant under a cyclic permutation of x, y, and z. If all the x's, y's, and z's take one step to the right, or if they take one step to the left in their ordering, then this polynomial is going to have the same value that it had before. Meanwhile, on the other side of the coin, every transposition of an x with a y, or a y with a z, or an x with a z, is going to change the value of this, and it's going to change it to its alter ego, x squared y plus y squared z plus z squared x. Notice a big difference here is which of the factors is being squared in each one of the terms. So I'm going to call these polynomials p and q. And these are the simplest possible Z mod 3 polynomial invariants that we can build that are not also S3 polynomial invariants. In other words, they're not fully symmetric, but they are symmetric under the cyclic subgroup action. Okay. So we're going to hang on to P and Q. These are going to play an important role for our process.